Good morning, dear students. Welcome back to Target JEE Class 12 Physics. We are in first lesson Electric Charges and Fields. Today we are going to discuss the concept of electric field. What is electric field? The nature of electric field is it applies force on static charges. That is the nature of electric field. It exerts force on static charges. And that is the nature. What is the definition for the electric field? Definition for the electric field is force per unit positive charge. That is the definition of electric field. So electric field is a vector. E bar is equal to F bar by Q. This is the formula as per the definition of electric field. E bar is equal to F bar by Q. But this formula is not 100% correct. Why? Because, see, let us take a source of charges. Whenever source of charges are there, electric field lines spread radially from this charge, normally from these charges. So this is the electric field. This electric field we want to measure. To measure, we have to put a positive charge. So if I put another positive charge here, plus small q, to calculate this electric field, because of repulsion, the position of source of charge will move back because of repulsion. So the actual distance between the source of charge and my charge I could not calculate perfectly. That's why my answer becomes wrong. So how to deal with this problem? Because we are, if we use that formula as it is, we are not getting exact value of electric field. So the Q, whatever the Q charge we take, the Q should be infinitesimally small. That infinitesimally small charge is also called as test charge. The symbol we use for the test charge is Q naught. So this formula will be correct if we write this formula as limit of F bar by Q when Q tends to 0. That means F naught F bar by not the unit positive charge, unit test charge. If we give if we put a unit test charge, very almost its value is near to 0, very small charge, so that it won't the test charge won't disturb the position of the source charges. Then by using this formula we can calculate electric field. So electric field formula, force per unit test charge. So what will be the SI unit for the electric field? The force per charge. Newton per coulomb is the SI unit. What is the dimensional formula for this electric field? Newton is a force. So force dimension formula ml t power minus 2, and coulomb charge dimension formula at power minus 1. So we get ml t power minus 3 and a power minus 1. This is the dimensional formula of electric field. We cannot visualize the electric field, so we draw electric field lines so that we can understand the electric field. So we know about electric field lines, how the positive charge around the positive charge, these electric field lines normally spread in all directions. So these are the electric field lines. For negative charge, these electric field lines will come will converge towards the negative charge. So, like this, electric field lines spread around a charge. Positive charge electric field lines, negative charge field lines. These always be normal. So, we can write electric field is the electric field magnitude into n cap. Like this, we can denote the electric field. This is the magnitude, this is the direction, always normal to the charge or surface of a charged body. So if positive and negative come closer like this, if positive and negative, they will attract each other. Why? Because electric field lines will go from positive to negative like this. So this electric field lines will spread like this between negative and positive. So about the electric field lines, what we can know is these electric field lines are they are not closed loops. They will start at positive and they will end at negative. Let us see some of the properties of electric field lines. See, field line is electric field line is path traced by a unit positive charge. So that is one of the property. Next property is it starts from positive and end at negative. So they are not closed loops. So they are not closed loop. They start at positive, they will end at negative. Third point. See, if I take a point P and draw a tangent to the direct tangent at this point to this field line, this will give the direction and magnitude of the electric field, right? Tangent drawn at a point on electric field line gives the direction of electric field at that point. So last property, they always repel each other. That means they never intercept. So they always repel each other. Why? Because these are the path traced by unit positive charges. That's why they always repel each other. So they never intercept each other. These are the properties of electric field lines. This is the formula of electric field. Electric field nature is applying force on static charges. Its definition we saw, and what are the flaws in that formula F by Q we came across. Let us look back the nature of electric field. It applies force on static charges, not on moving charges. The electric field is a vector quantity. Electric field is a vector quantity. So the direction is from positive to negative. If it is positive, this is negative, this is the direction of electric field. This is electric field direction plus to minus. In this field, if I place a plus charge, plus Q charge, the electric field applies the force on the static positive charge in the direction of electric field. The force applied by this electric field is the product of charge and the electric field. This is the force applied on the positive charge by the electric field. The force will be in the direction of electric field itself. If there is a negative charge here placed in this electric field, on this negative charge, this electric field applies force in opposite direction of the direction of electric field. It applies the force which is to the opposite direction of electric field. So here also the force formula is Q into E. So magnitude of force is equal to Q into E. So this is the force this electric field exerts on a static field. See, suppose for example, many a time in exams, NEET exam, they are asked, this is a pendulum. This pendulum is having mass m and given plus q charge, and it is oscillating. So oscillating pendulum time period is equal to 2 pi root L by G. Now I have placed a sheet having positive charge. If it is so, then what happens? This is the pendulum. Downwards, its weight is acting. See, this positive electric field is positive to negative. So the direction of electric field is positive to negative. This is the direction of electric field, right? So if electric field is also there, here positive q charge is there, this electric field applies the force on this positive charge in the direction of electric field. So here the force is q into E. This force will be there. This is the pendulum bob. So on this pendulum bob, two forces are acting, weight and the electric field. Because of this, G value, effective G value changes. How? See, this is a down G, this is up, minus, see, force is equal to QE. F is equal to MA if I write. A is equal to QE by M. This is the acceleration with which whenever force acts on a body, it acquires acceleration. So if any charged particle is there in the electric field applies force. Because of the force, the acceleration acquired by the charged particle formula is QE by M. So here the electric field is in opposite direction, G is in down direction, so we'll write QE by M. So this is the effective G. So like that here the time period changes. In the place of G I write 2 pi root L by G effective. If the pendulum is there having positive charge, mass m, the electric field direction is in this direction. This is the direction of electric field. Then what happens to the effective gravitational acceleration due to gravity, effective acceleration due to gravity, G effective is equal to, see, this direction mg is there, in same direction because it's a positive charge, electric field applies force in the same direction of electric field. This is a QE. So effective G value, G effective is equal to G plus QE by M. So, if you've been asked in the problem, calculate the time period, so G effective you have to take. See, direction of electric field you have to see. If the direction is like this, then the G effective formula is this one. If electric field is C, electric field is upwards. If electric field is downwards, then the G effective is this. Suppose this is a ground, a charged particle plus Q is projected into air making angle theta. But here positive charge is there. So on this positive charge, electric field also acting. And downwards its weight is acting. So when it been projected into air, at some point P, the G effective is equal to, see, mg is downwards and QE is upwards. This is the force exerted by the electric field on the positive charge. Always, if positive charge apply, this electric field applies the force in the same direction of electric field. That's why G effective is G minus, right, QE by this M, right? Actually, this is a negative one. Why? Because the G is acting downwards. So as the G is acting downwards, negative y-axis, we put negative here. If this is x-axis, this is y-axis, a negative charge is projected into air with angle theta with the initial velocity u, and here positive charge is there. The electric field direction is upwards and mg is acting downwards. Here it is negatively charged body. That's why if I take a position P of a particle on the trajectory of a projectile, what happened? Here in the downward direction, weight of this charged body is there. See, negative charge. On negative charge, electric field applies force in opposite direction to the electric field. That's why in same direction, it will apply the QE force. So in this case, G effective will be, G is downward, acting in negative y-axis, negative of G minus G plus QE by M. Like this, the formula will change. So be careful while you are applying this electric effects of electric field in various conditions. Let us see what is the electric field due to a point charge. Let us consider a point charge here, point charge Q. At r distance, at point P, the electric field direction, see, it is positive, the electric field goes away from the positive charge. The electric field here is K, this Q by this R square. This is the formula. K value we know. K is, this K value is 1 by 4 pi epsilon naught Q by R square. So this is the permittivity. Permittivity of free space. So we know that permittivity is a property of a medium. So between the point where we are calculating the intensity of electric field or strength of the electric field, between the point charge and the point P, whatever the medium is there here in between, that will be affecting the value of the magnitude of electric field. So magnitude of electric field depends on the medium. When medium is there, we have to take in the place of permittivity of free space, we have to take the permittivity of the medium. So that is the thing. And this 1 by 4 pi epsilon naught value, we know 9 into 10 to the power of 9 Newton meter square per coulomb square. So here the formula for point charge E is equal to kq by r square. Formula, let us write vector form. E bar is equal to kq by r square into r cap. This is one formula. And one more vector form is E bar is equal to kq by r cube r bar. Electric field due to extended body. So we are having a big body here. So many charges are there on it. So I have taken a small area. There small charge is there. From that, at r distance point P, the electric field. See, the electric field is because of the small charge. That's why that dE is equal to k dq by r square because of small. I have done like a big one here, very small portion of the body we have to take. Just for the visibility, I have drawn a big one, right? So how to calculate E? By integrating dE, we'll get the electric field of a extended body. Now point charge. Electric field formula kq by r square. So electric field inversely proportional to the square of the distance from the point where we are calculating the electric field to the charge presence. So it follows the inverse square law. So if you draw a graph here, this is x-axis. On x-axis I have taken r values. On y-axis I have taken E values. So when you go away from the charge, the electric field exponentially decreases. It never becomes zero. This is for a point charge. What if an extended body we have taken? So I have taken conducting sphere. Conducting sphere. So if I give a charge to a conducting sphere of radius r, this is the body on the, this is the point on the surface of a body. If I give charges, because of the repulsion, all the charges always resides on the surface of a conducting sphere. So inside the sphere, the electric field is zero because no presence of positive charge. This is a point on a surface of a sphere, and another point I will take at r distance, this point P. So this electric field inside is equal to 0. Electric field on surface of the conducting sphere is K. Let us take the charge here is capital Q, more charge is there, kq by distance, the radius r square. Here away from the outside, that means small r is greater than capital R, then formula kq by r square, right? So very much greater than or greater than r. So these are the formulae. So how can we get the graph for this? So this is x-axis, this is y-axis, this is origin. Here the distances we have taken, here the electric field we have taken. See, if you see the all three equations, this is the maximum electric field. So maximum electric field you can see on the surface of a conductor. So maximum value is kq by r square. So inside 0, the maximum value will be on the surface of sphere. So on the surface of the sphere, this is the r distance, from the center r distance. Here the electric field value is maximum, then it goes on decreases. Let us take a non-conducting sphere. Non-conducting sphere. So I have taken a sphere of radius r. This is a non-conducting sphere, insulator, bad conductor. So there is a restriction of electrons to move. So the electrons won't move here and there. So charges won't be flowing from place to place. Whatever the charge I have given to it, they stay there only. No change. So inside also electric field is not zero, and outside also electric field is not zero. So what I take a small point at x distance. This is point A, which is inside, and I have taken another point S on the surface of the sphere. Radius of the sphere is r, right? Another point I have taken, which is at r distance. This is outside P. So our inside also electric field is not equal to 0, and outside also electric field is not equal to 0. Then what would be the values? See, electric field at x distance from the origin. This is the center of the sphere. From the center at x distance at point A, I will write it is at A. The electric field at A, how much distance A is having from the center? X distance. The formula is K. Let us take the charge here is capital Q, very big charge is there. KQ x by R cube. KQ by R cube into x. That is the formula. Don't forget that formula. Electric field inside the non-conducting sphere at x distance is kq by r cube into x. From this, what we came to know, inside the sphere E proportional to x distance. Then electric field at the surface of a non-conducting sphere. As usual, that formula is kq by r square, right? This is the maximum value. Then outside at r distance, kq by r square. So here inside 0, here inside is not 0. The electric field is directly proportional to x, right? See, if we go from the center of the sphere to away, then what happens? The number of charges goes on increases. The charge enclosed goes on increases. So the electric field also goes on increases. So if you draw a graph here for non-conducting, this is x-axis, this is y-axis, this is origin. The maximum value is kq by r square, right? This is capital R. On x-axis I have taken R values, On y-axis I have taken electric field, capital E values. So here from 0 means from the center of the sphere to the surface, the electric field linearly increases. After that, it exponentially decreases. So these points are very important. Often they ask. Now let us see the principle of superposition in the case of electric field. Let us take a point charges. Here one point charge is there plus q1. Here another point charge is there plus q2, and here another point charge is there plus q4. So here I have taken a point P. At point P, the resultant electric field due to the charges we have to calculate. See, the electric field relating to Q1 at P is independent of the electric fields created by other electric charges. See, this electric field also acts along the line joining the centers. So this is the P. So in this direction, this is positive charge. So electric field will be radially going outside. It is diverging. This is because of first charge. And here, this is this is Q3. So here, this is the line joining the 2 points. So this is so I will write the P here. So P. So this is the electric field due to E3, and this is the line joining these two points, and this is the direction of E2. So these are the electric fields acting at P. E1 won't be the E1 electric field won't be disturbed by the electric fields A2, A3 because of other charges. So according to superposition principle, the net electric field is equal to the sum of electric fields at a point. So at this point P, the net electric field at point P. So I may also write EP, net electric field at a point P is the algebraic sum of E1, E2 and E3. So now only 3 are there. So 3 electric fields. If so many are there, we can also add all of them. Right? Like this, in the case of electric fields also, we can apply the superposition principle. Let us take 2 point charges. At A, 1 point charge is there plus Q1. At B, another point charge is there plus Q2. So the separation between these two charges is 2R, and exact at the midpoint, you've been asked to calculate the net electric field at O, a midpoint. See, whenever in any problem, if you've been asked to find the electric field, wherever you want to calculate the electric field at that point, you just assume that one point unit positive charge is there. At this point, one unit positive charge is there, like that I think. At this point charge, this is a negative charge. One positive charge, one negative charge is there. So this positive charge will repel this positive charge in this direction. That is the electric field at O due to the charge present at A. This negative charge will attract this positive charge towards it. So this is the electric field direction due to the charge at B. So now the net electric field at O is equal to EA plus EB. because both are in a same direction. If they are in opposite direction, so you take obviously negative there. Both are in same direction, so the net is addition of two electric fields. The distance between them is r. The midpoint is at r distance. It is also r distance from A. So EA is equal to, so electric field between them is 2 electric field between them K, this is Q by distance r square plus, here we are taking only magnitudes, no need to take negative here. When we are adding this negative mark, you should not write. Be careful on this point. And kq by r square. So net electric field is 2kq by r square. This is the net electric field at point O. Like this, we can calculate. One more example, let us see. One square is there. Each side length is A. This is position A, position B, position C, position D. These are the vertices of a cube, a square. So at this point, a positive Q is there. At this point, another positive charge Q is there. At this point, similar positive charge is there. You've been asked what is the net electric field at D. So here at D, we imagine that one unit positive charge is there. So if positive charge is here, this positive charge will repel this positive charge at D in this direction. That is the direction of electric field due to charge present at A. And this Q also repels this positive charge here. So the electric field here is like this. That is the direction of electric field at D due to the charge present at C. These two are in 90 degrees. The angle between them is 90 degrees. So what we know, if any force, this is one force, this is another force, angle between them is 90 degrees, then the resultant force formula is root 2F. This already we know in the vectors. Here in the place of forces, electric field is there. If this is the electric field E, this is also electric field E, both are in 90 degrees, then net electric field is root 2 E. So whenever they are 90 degrees, if they are vectors, we use that one. So in this direction, the net, both of them, see, both are Q, distance is A only. See VA formula, K Q by A square. This is also K Q by A square. Both EA is equal to EB. That's why in this direction, root 2 E will be there. E is the resultant of these two. At the same time, see here, one more charge is there at B. This positive charge also repels this positive charge. What is the distance between this D point and B point? This is A, this is A, it is a right angle triangle, this is the hypotenuse. So this is root 2 A. So this also be working here. This is the electric field due to charge present at B. So here net electric field at D point is equal to these two added, so this is root 2E plus this is electric field due to the presence of charge at B. So here root 2, what is the E value here? K Q by A square plus EB. EB is equal to how much? 2, sorry, K Q by K Q by the distance root 2A, root 2A whole square. So here root 2A whole square, KQ, root 2 square is 2A square. So I will take KQ by A square common, then root 2 plus 1 by 2 will come. This is the net electric field at D. Like this we can calculate in various cases. So next point. Another important point here to discuss is null point. Often they used to ask in JEE exams. Null point is that point where the net electric field becomes 0. So two cases we will discuss, and let us see how we can calculate the null point. For JEE and NEET exams, this point is important, right? So let us take 2 point charges here. This is plus Q, Q1 I may say, this is plus Q2. Both are not equal, they are different values, Q1 and Q2. So in between somewhere here, the net electric field becoming 0. The distance between them is R, and from Q1 the net, that null point from Q1, the null point is at X. Like that we can take. Now we have to calculate the null point. Null point means total net electric field there becomes 0. How? See, here at null point we assume a point unit positive charge is there. At point at n point we assume that unit positive. At null point n, wherever we want to calculate the electric field, there we assume a unit positive charge is present. So here unit positive charge plus is there. This plus will repel this one in this direction. So this is the electric field. I may give some names to the position A and B. This is the electric field due to the presence of charge at, if not this is Q1, let us write this is E1. And this Q2 charge is repelling this positive charge here in this direction. This is E2. So null point means magnitude of E1 is equal to magnitude of E2. I am not writing any bar over it, that means it is magnitude only. So these two magnitudes if equal, then net becomes 0. So wherever at point the net becomes 0, net electric field, that point we call it as a null point. So here E1, let us write the formula here. This E1 is between Q1 and N. So K Q1 by distance is x square plus here from neutral null point to Q2, K Q2 by this distance is R minus X. So this is R minus X whole square. So this R minus X I will bring here, R minus X whole square by X square is equal to this K and this K will cancel. Here Q2 will be there and Q1 goes there. I will take a square root, then this is R minus X by X is equal to, here root comes Q2 by Q1. The X is the distance to the null point from Q1. X is equal to what happens, root of R by root of Q2 by Q1 plus 1. This formula you remember, this is the distance of null point from Q1. Always remember here Q2 is big one, Q1 is small one. Always big one, small one. So distance of null point from small charge. If they ask the distance of null point from Q2, then use they just simply R minus X. See, distance of null point from Q2, that is big charge, is equal to R minus X. X value is there here. Like this we can calculate the null point. If see here, like charges are there, like charges. If unlike charges are there here, this is plus Q1, this is minus Q1, minus Q2. You remember always the null point will be outside the system of charges. This is the system of charges. This is A, this is B position. The distance between them is R. Null point always outside. This is N for null point. So this is X here and this is R plus X here. The distance between them is R. So don't forget, like charges X R minus X, unlike charges X R plus X. So I won't derive once again the formula for this. You just remember like this: null point distance from Q1, that is small charge, X is equal to this relation. If you remember so easily with lightning speed, you can answer the questions there, you can solve. X is equal to R by root of Q2 by Q1 plus R minus 1. So you remember, if plus is there, these are like charges. Like charges means these are the like, this is the case. Plus here, here also plus. A minus you ask when in the case of unlike charges.